Alright, so for today's video, we have a completely new topic for us. We've been talking about polar coordinates and some calculus techniques like finding the area on a polar graph, all in polar coordinates. And so today this is totally different. Topic here is parametric equations, okay? And I wanted to give an example of what parametric equations are, and also just think of an analogy to go along with it. Because on one hand, I can say, here's what parametric equations are. If I give you some number t, you can calculate what x and y are. And then x and y exist in two-dimensional space on graph paper where there's an x-axis and a y-axis. Okay. And t is called the parameter. All right. Now, as an analogy to that, though, that may be what parametric equations are, but as an analogy of that, you can think of an object that's moving in, let's say, 2D, and what I mean by that is two-dimensional space, okay? So you could say, all right, well, so if something was moving, at every time, it's at a place, and so there's actually three variables to keep track of. There's t, the time, and then there's the x and y coordinates of the position or the place. So you could think of something like this as being like that, right? I give you t, and you put it in these equations, and you get x and y. And at every time, there is a place. All right. So out of that, we might get concepts like, well, everything that moves along a path. So that's one concept that's involved in this. And everything that moves in a certain direction. And it moves at a certain velocity or speed. And the list goes on for there, but those are some basic concepts that will be involved in what we're doing with parametric equations. Okay, so that's where we begin. All right, now let's start going in the direction of the concepts. What would it look like if something was moving according to that, right? If at any time it was at that place. Can you sketch a graph and indicate what's called the orientation? All right, well, so here's how we can do that. In this example, I limited the parameter interval, the range, the interval that the parameter can be within, to be between 0 and 2. All right, so I will have to sketch my curve, my graph, in accordance with that, all right? But we might make a table like this. This is sometimes what we do when we sketch a graph. We just need some sample points, and the sample points would suggest what the entirety of the graph looks like. And if my t gives me x and y, and in this time t is limited to be between 0 and 2, then it's at least not crazy to think that I could start this way. I'll say, I'll make a table as t goes from 0 and then to 1 and then to 2. That's 3 sample points. That might be enough. All right, now when I do this, when I get my x and my y, I just put my t's in here, right? And I do the math, and I get x and y. Well, so that's not that hard to do with this one. I'll get -4 and 1. So at time t is equal to 0, I'm at position -4 for x, 1 for y. And at 1, I'm at 1 and then 5. All right, I just did the math. And then at 2, I'm at 6 and 9, and so on. All right, so that might be enough to sketch the graph. If a graph happened to be really complicated, we might need more points. I could say generally the more complexity and detail that a graph has, the more points you need, but that's probably good enough. So let's see here. Let me see. I'm going to be careful with my scale. All right, so I think that's enough. Now, first point, -4 and 1. So that'd be left 4 and then up 1. That'll be about right there. Okay. Second point, 1 and 5. That will be about right there. And then third point, 6 and 9. Now remember, these are x and y. All right. Make sure that you see the difference between that and t. All right. This is the xy plane. This is like graph paper. So I'm just plotting the x's and the y's. And then 6 and 9 is that last point. And that will be, I guess, about right there. And I definitely see a pattern. I hope you see a pattern too. I hope that you don't look at that and think those points are random. They're not random. They're points that are all along a straight line. Okay, so that is what these parametric equations look like. Okay, that's the graph. Now, so I've got the graph. I might put a few more details. Okay, you see these points that I have? All right, you're here. You're at this spot when t is 0. And you're here. You're at this spot when t is equal to 1. And then you're here when t is equal to 2. If you think about my analogy of this being motion, right? Every time you're a place. So with that information then, I can add a little more detail to this. I can give what's called the orientation, or if you're really thinking of this like it's motion, we'll call that the direction. But these two things mean the same thing. Think of it like this. You're here, and then you're here, and then you're here. That suggests a direction, okay? For sure. And so you'll see the graphs drawn various ways, but one way is that arrows might be put on it, okay? So here I'm at least trying to put arrows, having trouble handwriting all of a sudden, but that go in that direction because that's the direction that you're moving as t advances on the curve. All right, so there's my graph right there. That's the amount of detail that we'll ordinarily want to see on a graph. Now, next thing is the path, okay? Now, the path is just an equation that is in terms of x and y. So the path is also called the rectangular equation of the parametric equations. So either way you look at it, you know, the path is just information about x and y, okay? We eliminate information about t out of it. Do you see how information about t could play into this? Like, could I get like a kind of a feel for the velocity or the speed of this object? Since information about t is built into it, well, I could say, well, it takes you 1 second to get from here to here, and it takes you another second to get from here to there, and it incorporates distance and time all into the same picture. Well, the path, or the rectangular equation, is just information about x and y. Of course, if I know some path you took to get somewhere, that wouldn't have any information about time in it. It would just be footsteps or something like that. There wouldn't be time. So to get the path, we will eliminate t out of our equations, and then we'll just be left with x and y. All right, so here's what I was working with. We'll use these together to try to eliminate t. So let me take that first one. That first equation I had up there was x is equal to 5t minus 4, okay? All right, that's what I started with. Now, if I solve that for t, then I'll get like so, okay? And then if I substitute that value of t into this second equation, I will have eliminated the t, okay? So it's like, take the first equation, solve for t, and then sub. And if we do that in that second equation, then it's going to look like this. Y is equal to 4t, but t is x plus 4 over 5, okay, plus 1. So that second equation was y is 4t plus 1. All right, so we use them together. Now, putting all this together in a more recognizable form, I might say we'll get this. We'll get 4/5 x, okay? And then this factor right there, that'll be 16 over 5, okay? And if I add 1 to that, so that will be 21 over 5. So I'll get 21 over 5. So there's my path, okay? So it looks like the path was a line, slope 4/5, y-intercept 21/5, okay? All right, so I'm going to put that all up here. I want to put it all together. The path of this, meaning the equation of this line right there, is y is equal to 4/5 x plus 21 over 5. I think that's entirely conceivable, right? I mean, where's this line seem to hit the y-axis? As I drew it, I tried to be careful with my scale, a little bit above 4. And 20 over 5 would be 4, so 21 over 5 is a little bit above it. And that's got a positive slope of 4/5, okay? All right, so that's like basic concepts with where we begin, okay? You got t, the parameter. You got x and y, your normal x and y coordinates, okay? You've got the graph. You've got the direction or orientation, and you have the path, all right? Now, let's look at a few more examples, though. Let's try one that I think is quite a bit different, but we can still practice what I was talking about, all right? So here, x and y given as functions of t, okay? X is t plus 5, y is root of negative 2 times t, and t runs from negative 5 to 0, okay? In part 1, can you sketch the graph? All right, and part 2, can you give the path? So I got the same arrangement here as the last one. Now, so let's start with the graph. I'll make a table because I think it's a easily accessible, easy to understand thing to do. All right. So I will put in various t's in here in my allowed, domain for the parameter. So t, and then I'll get x and y as calculated from this, okay? So maybe I'll start with negative 5, and I'm going to work my way to 0, but I want a few intermediate numbers, so I'll do like negative 2, and I'll do, I don't know, how about negative 1/2? I think that would be a convenient number, and then 0. How about that? Let's try it. So here's what you're going to get if you take these t's and put them in here for x and y. All right? So let's see. For negative 5 first, I'm going to get 0 and root 10. Okay. Root 10 being a little more than 3. And for negative 2, I'll get 3 and 2. Okay. And for negative 1/2, I'll get 9 over 2 for x, because I'm going to take t plus 5. So it'll be 4.5 if I do that, or 9 over 2. And negative 1/2, I'll get 1 for y, right? Negative 2 times negative 1/2, that's positive 1. Root 1 is 1. And then for 0, I'll get 5 and 0. So that should be enough points, but let's have a look. Let's have a look. What does this graph look like? If something really was moving around according to those equations, then how's that going to play out? Well, all right. So let's see. I'm going to go 1, 2, 3, 4, 5. So we're going to go as far that way. And maybe about up like so. Okay, first point, 0 and root 10. And root 10, and like I said, is a little bit more than 3, so I'll put that point right there. 3 and 2, so right 3 and up 2, about right there. 9 over 2 and 1, so that's 4.5 and 1, so about right there. And then 5 and 0, so that'd be right there. So that's everything. So I see like kind of a curve. These are not along a perfectly straight line this time. And to me, like I'm seeing something kind of like that. It's not, doesn't have some extreme amount of curvature to it, but it's a little bit curved, okay? So there's the graph of it. Now, what about the direction or the orientation? How does time advance on these points? You're here at the smaller time, t is negative 5, and then you're over a little bit at a slightly larger time, t is negative 2. So as time or as t advances, we're going that way. For bigger values of t, our points are moving to the right, all the way over here to when t is equal to 0. So the direction, we can just put these arrows like so, and that will give a feel for the direction. So there's the direction, okay? Is there some, is this part of some overall curve or something? What's the path, okay? Is there an equation for just what you see there? that leaves t out of it. Remember what the path is. The path takes our parametric equations and loses all the information that t would give. So we can find the path, or what's also called the rectangular equation, by eliminating t out of it. So can you think of a way to do that this time? I think we could do it the same way that we did the one just a minute ago. If I take my first equation, okay, which is x is equal to t plus 5, and I solve it for t, then I can put that into my second equation, okay? And my second equation says y is root negative 2 times t. So that would be y is root negative 2 times t, but t is given to be x minus 5. Okay, so let's give the path like this. Let's say this. I'm going to write it up here. Okay, I'll say root 10 minus 2x. That's the way that's going to reduce. Okay, so that is the curve that you're seeing right there. All right, it's not all of it. This curve is more extensive than what you see here. But if you took part of this curve between that point, 5 and 0, and this point, 0 and root 10, then that's what this would be. Okay? All right, now, so let me get, so there's my answer. This is the graph. It's got my orientation or direction and my path all in the same place. All right? So I got everything there all in the same place. I wanted to talk a little bit more about the interaction of this equation with what you see here in the t's. So I'll put note here. All right, so just this is kind of a remark that I might make after the fact, that now that I have this one done. Say, what about this curve y is equal to root 10 minus 2x? Okay, what is that? Well, that's a curve with a domain of x less than or equal to 5. Okay, so it actually looks like this if we had drawn it extensively. It's the curve root x with a horizontal reflection and stretching and all that kind of stuff, but it looks like this. Okay, it actually goes forever that way. The domain is negative infinity to 5. This point being 5 for x, 0 for y, and this point being, just to give another example, 0 for x and root 10y. Okay, so that's this curve in its entirety. I'm not saying, when I say the path of this is this, I'm not saying it's this whole thing, because as t only runs between negative 5 and 0, you only get this much. All right, so I don't want to mislead you about the path. Nonetheless, what you see here is this part of that curve. All right, it's just that the limitations on t don't give you the whole thing. All right, now what if there weren't any limitations on t? Well, then you'd maybe have the whole thing. All right, okay, but as it is that there are, that's what you're getting. All right, so that's just maybe some fine print about when I say the path is whatever it happens to be. I'll tell you what I mean by that. All right. Okay, so let's look at another one. Now, every time I do another problem, I'm kind of thinking about, I want to add just a few more details that we need to learn about in every problem. So here, this one even has details that the last one didn't. The equations certainly look different. And here I'm letting t be anything, okay? So in the first one, I happen to say, well, all right, let's just restrict t to be between 0 and 2, and you'll get this line segment. True, that line does go beyond what I have here. But as it is that t is limited, I'm only getting that much. All right, so this time t can be anything from negative infinity to infinity, which is any real number, okay? So, well, what do you think about that? Let's draw a quick sketch again. We'll see what we can get from the points. All right. points. So like, well, I don't know, t, x, y. We could do like this. -2, -1, 0, 1, 2. I mean, t could be anything. I think it'll be hard to go further outside of this, though. But if I wasn't seeing a coherent picture when I tried to graph it, I could go less than -2 and more than 2. Or even I could go between these numbers if I needed to, if I needed more details. But I think this will probably be good enough. So if t is -2, what are we going to get? We're going to get, so 1/4 for x, right? 2 to the -2 power. And then here, this will be 2 to the -6 power. If I put -2 for t right there, so that'll be -6, 2 to the -6 power. That's going to be 1/64. Okay. And what about -1? That'll be half and 1/8. Okay. What about 0? 0 is going to give me 1 and 1. Okay, from that. 1 will give me 2 and 8. And 2 will give me 4 and 64. All right. So that's probably plenty of points because like how am I even going to graph 64 and 1 on the same scale? Or 1/64th. That's extremely small to extremely large. Nonetheless, let's see what we get. Okay. I'll do the best we can on this one. Let's do like something like this. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's go no higher than that. That should be good enough. So 1/4 and 1/64. I'm not going to try to do that one. That's going to be too hard. A half and an eighth. So, okay, right a half and then up an eighth. That's going to be like right there, roughly, right above the y-axis, or the x-axis. Okay, and then 1 and 1. Okay, so that's going to be here. And then 2 and 8. All right, so that's going to be here. And then 4 and 64. Well, you can use your imagination. Okay, all right. So there, that's what we get. Now, I can see a pattern. It's not like these points look random, but I'm going to have to do some thinking outside of what I see in this table. All right. So let's think of some limitations here. I can kind of see the points going like this or something like this. All right. Or who knows, maybe over there. But think about it. As I let t run to -infinity or infinity, can x be negative? Like, would 2 to some power, whether it be positive or negative, would x itself ever be negative? No, 2 to a power will always be a positive number. If that power is negative, you'll get a fraction. If it's a whole number, a positive whole number, then you'll get something larger, but it won't be negative. It's the same thing with this one. So y is not going to be negative. Not going to go over here or down here. Okay? So, but let's see, where really are these going then? Let's do some limits here. So I notice the limit as t goes to -infinity to t is 0. So if I were to push the points on the table this way, the x coordinates would go to 0, never quite getting there. Okay? And same thing with this other one. The limit as t goes to -infinity, 2 to the 3t is also 0. Okay? So the y coordinates are also going to 0. If I had continued making this table that way, with t going towards -infinity, those numbers would just close in on 0 and 0. And that's as far as it's going to get. So I'm going to have to, that point will be open. You never quite get there. But that's where the points on my table were going. All right? So keep in mind, that point's open. And then they go off like very steeply like that. All right. Okay, so now that's a detail that we didn't see in the other tables. So the other tables with the other problems, I think like this told the whole story for the most part. But I really think to understand where to go from here, you'd have to see these limits for what the x and the y are going to do. All right, Now, that way, well, there's just the graph's going to climb upward. All right. So I've got that. I got something I'm happy with. What about the direction? Well, this point had t to be 0, and this point had t to be 1, right? So this was 0, this was 1, and the points were just tracking this way as t advanced. So there would be my direction, like so. Okay, so I got that. What about the rectangular equation? What's the rectangular equation? It's what I also called the path. The rectangular equation would eliminate information about t, okay? So, all right, let's see the way to do this one. Let's take the second equation and sub the first one into it, but I'm going to need to do some work on the second equation. So I'm going to write both of them down here. So we got x is equal to 2t, and then y is equal to 2 to the 3t. I think to substitute the first one into the second one, similar to a way that we did in the other problems, I'll do like this. Okay, and then I'll get this. Oh, wait, I don't need to go that far. Let's do this. There we go. That's more like it. Because that is x. So using the laws of exponents, I can separate the exponents. This is effectively an exponent of 3t, but I separated it out, and I see my x. X is 2 to the t power. So it's going to be y is equal to x to the third power. Okay? All right. So I've got x to the third power. That's this curve right here. Okay? So let's do this. Let's say our path, y is equal to x to the third power. And you might see something like if you're doing your homework or something like that, the fine print on the path might be, well, how do we indicate that we're not getting this entire curve, just this part of it? Okay? So think about it. The curve x to the third power, if you had the whole thing, that would be a curve roughly like this. Okay? And then we kind of have that up there. It's just we have this part of it, and we don't have the origin. All right? For reasons I talked about, you're not going to get the origin. It's not going to show up on the table at all. So let's say the path is y is equal to x to the third power for x greater than 0. Okay? All right, so here we have it all in one spot. The curve, the direction, that's what the arrows mean, some points labeled, this one being open will reflect that in the path, it's strictly x greater than 0, not greater than or equal to 0. Okay? So that's all about that one, all right here.